Welcome to Electrochemistry. My name is Stephen. Electrochemistry is a branch of chemistry. It deals with the chemical action of electricity and the production of electricity. This is achieved by chemical reactions through electrochemical cells. Electrochemical cells fall into one of two basic types. One is galvanic cells, which convert chemical energy into electrical energy, such as batteries. Second is electrolytic cells, which convert electrical energy into chemical energy. Consider a piece of zinc metal put into a copper ion solution. A reaction occurs where we get zinc ions and solid copper deposited on the zinc surface. This is referred to as oxidation reduction or redox process, where electrons are transferred from one chemical to another. One chemical loses electrons in a process called oxidation, while the other chemical gains electrons in a process called reduction. Since we actually see this reaction occurring, this reaction is spontaneous. And indeed, the reverse reaction, where we put copper metal into a zinc ion solution, is non-spontaneous. In the spontaneous reaction, we can see that each zinc atom gives away 2 electrons to a copper 2 ion to give us a copper atom and a zinc 2 ion. To clarify the redox process, we often break a redox reaction down into 2 separate steps known as half reactions. In one half reaction, a chemical loses electrons, or we say zinc atom has been oxidized. We call this the oxidation half reaction. Notice that we are effectively treating electrons as a product of the half reaction. In the other half reaction, we look at the reduction half reaction, where a chemical gains electrons, or we say copper 2 ions has been reduced. Note that the sum of these half reactions must give us the overall reaction of interest as shown here. Note that the sum of these half reactions must give us the overall reaction of interest as shown here. Remember this, for the half reactions, the electrons stay on the metal electrode and are never found in solution. Since the chemicals are in direct contact with each other, the electron transfer occurs directly, and we can't use the electrons to do anything useful. But then, how can we separate the chemicals but allow the electrons to transfer indirectly so we can use them? You shall be able to answer that sooner than later. Consider copper atoms in silver ion solution, which is a spontaneous reaction. The half reactions need to take place in separate containers called half cells. Since a half reaction cannot take place by itself, we need to connect the half cells together. It turns out that we must make a circuit of 2 connections for the entire galvanic cell to work as shown in the diagram. The left half cell has a solid copper electrode in a copper 2 ion solution, while the right half cell has a solid silver electrode in a silver ion solution. A wire connects the 2 solid electrodes for the electrons to move through, to connect the 2 solutions so that ions can move between the half cells. We require to use a salt bridge, which is just another solution of ions, in this case potassium nitrate solution. During the process, oxidation occurs at the copper electrode, which we give the special name anode, since the anode collects the electrons that are lost. It has a negative charge and positive copper ions leave the anode. Please note that electrons are moving from the anode to the silver electrode through the wire. From here we can get them to do something useful, such as lighting a bulb. On the other end, reduction occurs at the silver electrode, which we give the special name cathode, since the cathode collects the positive silver ions so they can gain the electrons. The cathode has a positive charge. Here, positive ions leave the anode while the cathode collects positive ions. Alternatively, negative ions collect at the anode and move away from the cathode. In fact, the ions are free to move through the salt bridge and are required to complete the circuit. Please observe that in overall, the negative charges, which we can call electrons or negative ions, are moving clockwise. Likewise, in overall, positive charges, which we can call positive ions or electron holes, are moving counterclockwise. The overall reaction is exactly the same as when we place solid copper in a silver ion solution. But since we have separated the half cells, we can look at the separate half reactions as they occur. Also note that the number of electrons must balance as shown in this equations. As a matter of fact, drawing a diagram for a galvanic cell, or describing it as we have done in the previous problem, is tiresome and time-consuming to do on a regular basis. Thus, we use a shorthand notation. From the notation shown here, a single vertical line indicates a change in phase, like that between a solid electrode and the solution it's immersed in. A double vertical line indicates a salt bridge. What is not shown in the shorthand but is always implied is the wire connecting the two electrodes to complete the circuit. If we read the shorthand notation from left to right, it says, a solid copper anode is in a solution of copper 2 ions, which is connected by a salt bridge to a solution of silver 1 ions, into which a solid silver cathode has been placed. The electrodes are connected by a wire. Point to note. We always choose to write the cell notation with the oxidation reaction first, and then the reduction reaction. This means the leftmost chemical in the notation is always the anode, while the rightmost chemical is always the cathode. Additionally, the electrons always flow from left to right through the wire, which is the way we read the shorthand. Observe this cell notation. Everything is clearly indicated as discussed earlier, including an arrow that show the flow of electrons through the wire connecting the electrodes. Understanding galvanic cells is easy as a BC. The anode is the negative electrode where oxidation takes place, and we put it on the left in shorthand notation. Likewise, the cathode is the positive electrode where reduction takes place, and we put it on the right in shorthand notation. Here is another point to note that sometimes gases are involved in galvanic cells. In such a case, including them in the shorthand is easy once we realize the gas is just a separate phase and must be separated from other phases by a vertical line. Consider this reaction of copper atoms reacting with chlorine gas. Since we can't use a gas as an electrode, we need some solid substance to do that job. In this case, we need to bubble the gas by a carbon rod. The cell notation with the carbon acting as the cathode is as shown by the second equation. Also, we can be more specific by giving concentration and pressure data for any of the aqueous or gaseous chemicals of the system as shown here. Here is a quick test. Write the shorthand notation for a galvanic cell that uses the reaction of iron atoms in tin 2 iron solution. Your answer should be as shown here. Second test. Write a balanced equation for the overall cell reaction and give a brief description of the galvanic cell represented by lead atoms in bromine water. Please note that the reduction of bromine atoms to bromide ions occurs on the surface of a platinum cathode. Let's now dive into cell potentials for cell reactions. Electrons move from the copper anode through the wire to the silver cathode. because it is energetically favorable for the electrons to move. Note that an electron in a silver atom has less free energy than the same electron in a copper atom. Much like a ball wants to roll down a hill, so it ends up where it has the lower potential energy. An electron wants to move to the atom where it has the lower free energy. Indeed, the difference in the free energy for the electrons in the anode and the cathode is somewhat like the slope from the top to the bottom of the hill. If the hill is steep, the ball experiences more of the force of gravity than it does on a gentle hill. Further, the equivalent of the force of gravity to the difference in the free energy of electrons in different atoms is called the electromotive force, or E.m.F., also known as the cell potential represented by capital E, or the cell voltage represented by capital V. Like a ball on a steep hill, electrons are under a greater force to transfer from the anode to the cathode when the cell potential has a larger magnitude. It's worthy to note that because there is a free energy difference for an electron in the anode as compared to the same electron in the cathode, the electron must lose free energy during the trip, just like a ball loses potential energy as motion as it rolls down the hill. The free energy change is negative, and so the movement of the electrons is a spontaneous process. The free energy change is negative, and so the movement of the electrons is a spontaneous process. This occurs when the potential is positive, so a positive potential indicates a spontaneous process. Also, we can get energy out of a ball with its certain mass rolling down a slope, i.e. the experienced gravity. Similarly, we can get energy out of an electron with electrical charge that rolls down the slope, that is the potential difference of electron-free energy between the two electrodes. In terms of units, we can define 1 joule as the energy we get from a charge of 1 coulomb multiplied by the potential of 1 volt. Note that a coulomb is a very large unit of charge. The charge on one electron is 1.60 x 10 power minus 19 coulombs, so 1 coulomb is the charge of about 6 billion electrons. It is generally easier to talk about the charge of 1 mole of electrons, which we give the special name of Faraday constant, or Faraday represented by capital F. We can measure the potential between two electrodes with a voltmeter. This should give a positive reading when the positive terminal of the voltmeter is connected to the positive electrode, or the cathode, and the negative terminal is connected to the negative electrode, which is the anode. When the voltmeter gives a positive potential, we have identified the direction of spontaneous change. Consider copper atoms in silver ion solution. This is a spontaneous reaction. But how can we define standard cell potentials? Cell potentials depend on many factors other than the chemicals in the system, including the temperature, ion concentrations, and pressure. We can only measure a standard cell potential if we have pure solids and liquids. All solution activities are at 1 mole per liter. All gas activities are at 1 atmosphere, and the temperature is specified, usually at 25 degrees Celsius. For zinc atoms to react with copper-2 ions, we can only measure the standard cell potential if the zinc ions and copper ions are both 1 mole per liter, and the copper and zinc electrodes are pure. In such a case, the standard cell potential for this cell will be 1.10 volts at 25 degrees Celsius. In short, The standard cell potential for any galvanic cell can be expressed as the difference of the standard electrode potentials for the cathode and the dianode. Still, the standard electrode potential depends on whether the electrode is acting as the cathode or the anode. However, the process at the cathode known as reduction is the opposite process that would occur if it were happening at the anode, i.e. oxidation. However, reversing a process changes the sign of the electrode potential associated with the process. Therefore, we choose to report all standard electrode potentials as reduction processes, because for any specific electrode, the reduction standard electrode potential at the cathode is equal to negative reduction standard electrode potential at the anode as shown. It's worthwhile to create a table of standard electrode potentials for all possible electrodes. Then we could find standard cell potentials for any cell. However, there is one problem. We've already seen that half reactions cannot occur without another half reaction. The problem is similar in thermodynamics when trying to define the standard enthalpy of formation of elements in their standard states as zero. Hence, we can do the same for electrode potentials and set the potential for a specific electrode as zero and measure all other electrode potentials in comparison to the standard. Kindly note that the standard electrode for potentials is the standard hydrogen electrode. The electrode consists of hydrogen gas at 1 atmosphere which bubbles through a 1 mole per liter solution of hydrogen ions past a platinum electrode. If the oxidation reaction occurs instead in this half cell as an anode, the overall reaction oxidizes hydrogen atoms into ions. Also note that reversing this reaction changes the sign of the potential. Consider this cell. The standard potential for this cell is measured as 0.340 volts at 25 degrees Celsius, where the anode used is the standard hydrogen electrode. So far we have defined the standard electrode potential of the reduction of copper to ions to solid copper metal. This is also known as a standard reduction potential. Otherwise, if we reverse the half reaction, we will get the standard oxidation potential for the oxidation of solid copper to copper 2 ions. Have a look at this cell. The standard potential for this cell has been measured as 0.763 volts at 25 degrees Celsius, and the anode used is the zinc electrode. Further, we found the standard potential of the oxidation of solid zinc to zinc ions. Such a reaction shows standard oxidation potential. In fact, if we reverse the half reaction, we will get the standard reduction potential for zinc 2 ions to zinc metal as minus 0.763 volts. Such a value is reported as the standard electrode potential. Similarly, the standard cell potential for this cell can be calculated if we know the anode, which is the zinc electrode, and the cathode, which is the copper electrode. Have a look at this tabulated standard electrode potentials. Using tabulated standard electrode potential data is accomplished much like an Hess's law problem, with one very important difference. Consider the oxidation of zinc metal by silver ions. The reaction is as shown by the cell notation with its corresponding balanced chemical equation. For the previous reaction, the zinc metal is oxidized into zinc 2 ion solution. Simultaneously, the silver ions are reduced into silver metal. This gives a 1.563 volts reading on the voltmeter. In short, like Hess's law, we have looked up the standard electrode potential reactions for both sets of chemicals. We then reversed the half reaction for the set undergoing oxidation while changing the sign of the electrode potential. However, we did not multiply the potential for either half reaction. But why? Here is the reason. You can recall us discussing the potential as the slope of a hill. In essence, a hill does not change its slope if we have two or more balls rolling downhill, instead of one ball. Therefore, in this case, the potential of an electrode does not change if we multiply to get the right number of electrons. Here is a problem for you to try. You are that the standard cell potential for the following galvanic cell as 0.78 volts. The standard electrode potential for the aluminium electrode is minus 1.676 volts. Calculate the standard electrode potential for the chromium electrode. You should get your answer as minus 0.90 volts. Let us now shift to free energy in electrical work. The constant of proportionality must depend on two things. First, it depends on how many electrons we have moved through the wire. Twice as many electrons should mean twice as much work. We usually measure numbers of electrons in moles and symbolize it by letter N. Please, attempt this question. When sodium metal is added to seawater, which has a concentration of magnesium ions as 0.0512 moles per liter, no magnesium metal is obtained. According to the data given, should this reaction occur? What reaction does occur? Here is the answer to the problem. For the reaction, sodium atoms reduces magnesium ions and the reaction should be spontaneous. However, the reaction of sodium with water has a high standard electrode potential, and thus the reaction should also be spontaneous. Since the later reaction is more spontaneous, sodium preferentially reacts with water and not magnesium ions. Here is another problem. Without using the data for a detailed calculation, explain why tin 2-ion solutions must be protected from oxygen. One way to protect them is to add metallic solid tin. The answer is, for both possible reactions, the reduction of oxygen is the cathode half-cell reaction. The anode half-cell reaction, that is more negative. It will give the higher, more spontaneous standard electrode potential reaction that will preferentially occur. Let us now focus on how metals react with acids. Some metals will react with acidic solutions to form hydrogen gas and metal ions in solution, while others will not. We now know that those metals that do react with acid do so because the reaction is spontaneous. On the other hand, those that do not react is because the reaction is non-spontaneous. In most cases, the reduction reaction of metals in acidic solutions is the reduction of hydrogen ions into hydrogen gas, giving a 0 volts reading on the voltmeter. As we discussed earlier, this is the standard hydrogen electrode half reaction. If this is the preferred reduction or cathode reaction, and since a spontaneous process must have a positive potential, then for a metal to react with the hydrogen ions of an acid means as shown here. The metals that can react with hydrogen ions are the ones with a negative electrode reduction potential value like sodium, aluminium, or even lead. The metals that cannot react with hydrogen ions of an acid have a positive electrode reduction potential value, like silver, gold, and copper. Please note that some acids, like nitric 5 acid, have a different preferred reduction or cathode reaction as shown here. If the previous is the preferred reduction or cathode reaction, and since a spontaneous process must have a positive potential, then for a metal to react with the nitrate ions of nitric 5 acid means the electrode reduction potential of the anode must be less than 0.956 volts. In nitric 5 acid, all the metals that usually react with acids will still react, but now the reduction of silver will also take place. Let us now see the standard electrode potential as a function of concentration. We can see that the standard electrode potential of the given cell is 1.103 volts at standard conditions. However, what happens to the cell at non-standard conditions? If we set up this cell and measure the potential, then the standard electrode potential is 1.142 volts. But why? Here is the explanation. Since the actual reaction is reduction of copper ions by zinc atoms, then Le Chatelier's principle tells us that decreasing zinc 2 ions from 1 mole per liter to 0.10 mole per liter should shift the reaction towards products. Likewise, increasing copper 2 ions concentration from 1 mole per liter to 2 moles per liter should shift the reaction towards products as well. It's good to note that the reverse of every spontaneous chemical reaction is non-spontaneous. If we apply electric current to a chemical system, it is possible to force non-spontaneous chemical reactions occur in a process called electrolysis. This is what we call electrolytic cell. The potential we apply to the electrolytic cell must be greater than that for the spontaneous reaction. It must also be applied in the opposite direction. Consider a zinc metal placed into a copper 2 ion solution. Since we can actually see this reaction taking place, this reaction must be spontaneous. The reverse reaction, where we put copper metal into a zinc 2 ion solution, is non-spontaneous. Also, if we want to get zinc from this cell, we must force the non-spontaneous reaction to occur. This is achieved by applying a potential in the direction opposite that for the spontaneous process. In that case, reduction always occurs at the cathode. Let's now discuss electrodes. Platinum is an inert electrode that only provides a surface for the true reactants to transfer electrons. An active electrode is an actual reactant in the half-cell reaction. Note that using a different electrode on one side of the electrolytic cell, it might change the half-cell reaction on that side. Consider this quantitative aspects of electrolysis. Please observe how the chemical decomposition reaction is produced by passing an electric current through a solution containing sodium and chloride ions. If we pass 1 mole of electrons through the previous cell, we will get 1 mole or 23 grams of solid sodium out. At the other electrode, where chloride ions are oxidized to chlorine gas, we see that 1 mole of electrons is enough to give us 1/2 mole or 35.5 grams of chlorine gas. Here is another point to note. During electrolysis, the number of electrons passing through the cell depends on 2 factors. One is the current, which is the charge per unit time, i.e. coulombs per second, simply put as amperes. The second factor is the time the current was allowed to pass, though the cell measured in seconds. Recall that we earlier saw that 1 mole of electrons has a charge equal to 1 Faraday. which is equivalent to 96,500 coulombs per mole. Hence, to find the number of moles of electrons deposited during an electrolysis process, we divide the charge by the number of Faradays. Please observe the given flowchart showing how to find the amount of substance that comes from electrolysis based on a known current and time. If we want to know the current or time used to get a certain amount of substance, you just reverse the order of the flowchart. Attempt this problem. How many kilograms of aluminum can be produced in 8 hours by passing a constant current of 100,000 amperes for an electrolytic cell with the following half reaction at the cathode? See if you get an answer of 268 kilograms. Last question. A layer of silver is electroplated through an electrolytic process on a coffee server using a constant current of 0.1 ampere. How much time is required to deposit 3 grams of silver? Again, see if you will get 7.45 hours as your final answer. That brings us to the end of this topic, electrochemistry. Thanks for watching and learning with me. See you in the coming topic.